Welcome to lecture number 23 of my series PH 4105 Advanced Mathematical Physics. In the last few lectures, we had met tensors and their corresponding tensor fields. In particular, we had met a 0k tensor. At a point P on the manifold, a 0k tensor is a multilinear map from k copies of the tangent plane of the manifold M to R. What that means is, if you feed a tensor of type 0k, k tangent vectors at the point P to M, it's going to yield a real number, and this map is going to be multilinear in the sense that if you were to replace any one of the arguments by a linear combination, the output number will be the corresponding linear combination of the inputs. Now, with the notion of a 0k tensor comes the associated notion of a 0k tensor field. This assigns to each point P on the manifold or to a point P in a subset U of M, if the tensor field doesn't happen to be globally defined, a 0k tensor at the point P. Now, a 0k tensor field T acts on k vector fields on M to yield a function on M. And the definition of this function, T acting on x1 through xk, is as follows. This function, evaluated at the point P, is defined to be the result of acting Tp, the value of T at the point P, this particular 0k tensor at the point P, on the values that you get when you give the P as an argument to these vector fields. That is, the corresponding tangent vectors at the point P which these vector fields yield at the point P. Now this, of course, is a real number, and thus what this whole expression does is assigns to a point P on the manifold a real number. So it's a function on the manifold. Now, we will call the tensor T smooth if for all smooth vector fields x1 through xk, the resulting function T acting on x1 through xk is a smooth function. Now, a particular result that was of great importance and will be of great importance today, as you will see, is that if we are talking about a coordinate patch, a chart u, phi with coordinate functions x1 through xn, the tensor field, a 0k tensor field in particular, can be expressed in the form ti1 through ik, dxi1 tensor product with dxi2, all the way up to tensor product with dxik. Here, of course, what you are doing is not only multiplying this function through this tensor product of coordinate differential one forms, you are also, of course, summing up over all the dummy indices. Now, these functions ti1 through ik, which sit as coefficients of this, is given simply by the action of t, a tensor, on the coordinate differential vector fields del xi1, del xi2, all the way up to del xik. If you are given these n to the power k component functions, you actually have complete knowledge about the tensor, at least within that domain U. Now, if you have multiple charts available, and in particular the domains U and U prime of two charts overlap, then in the overlap region you could use either the coordinates x1 through xn or the coordinates x prime 1, x prime 2 up to x prime n from the other chart. And in such a case, these tensor components will transform, and the transformation law happens to be a very familiar law that we have all seen in physics. Now, today's lecture will be on 0k tensor fields, but on a rather special kind of 0k tensor fields. These are called differential forms. Now, you may wonder that if the differential forms are actually 0k tensor fields, then why are we bothering to study them separately? We have already said quite a lot about 0k tensor fields. It so happens that because of the special demand you make in order that a 0k tensor field qualify as a differential form, it turns out that these objects have immense importance in mathematics and mathematical physics. Now, let us take a look at exactly what constitutes a differential form. A differential K form, omega, defined on a manifold M, is a completely antisymmetric differentiable 0k tensor field on M. So not only does it have to be a 0k tensor field, that's something we have already said, it also has to be differentiable, and most importantly, it has to be completely antisymmetric. What this last qualification means is the following. When you feed omega k vector fields, you are going to get a function. And in particular, because omega is a differentiable 0k tensor field, whenever these k vector fields are smooth vector fields, this resulting function has to be a C infinity function. But complete antisymmetry tells you the following. If you were to interchange any of these two arguments, for example here, I am interchanging these two arguments xi and xj to get xj and xi in their respective positions. That is going to produce a minus sign. That's what completely antisymmetric means. Interchange any two arguments, you are going to get a negative sign. Of course, this has an immediate consequence that if you were to have a situation where both of these arguments, xi and xj, any two of the arguments given to omega are identical, then omega must be negative of itself, which means the function that you get in such a case will have to vanish. And this has to happen not only for any given ing, it has to happen for all ing where I can be 1 or more. J of course is larger than I because that's why it's sitting to the right in the original expression, and j can be all the way up to k. Now, some special cases, a zero form is basically a 0,0 tensor field, and in such cases, differentiability essentially implies that it has to be a C infinity function on M. Antisymmetry makes no sense because there are no arguments that you can give such a tensor field, which is just a smooth function, and therefore antisymmetry is trivial here. Another case where antisymmetry is trivial is where you have only one argument. Of course, in that case, interchanging two arguments does not make sense. So, what you get in that case is a 0,1 smooth differentiable tensor field, or a 1 form. A K form, of course, is a generalization of that. To summarize, the two special cases are a 0 form is simply a function by definition, and a 1 form is something we had already met before. It is a smooth covector field. Now, if you are given a smooth 0k tensor field, not necessarily completely antisymmetric, you can construct a K form from that. And this is a construction that's going to be very important in later definitions. For this, we need to introduce some notation. Sk here stands for the set of all permutations of K objects. This actually happens to be the so-called symmetric group, because the set of all permutations have this additional property that they form a group, but that's really not that important right now. We will also denote by sign of sigma, Sg and sigma, the sign of the permutation sigma. What that means is that if you can get to this particular permutation by doing an even number of interchanges, then sign sigma is going to be +1. If it needs an odd number of interchanges, then Sg and sigma is going to be -1. So given a smooth 0k tensor field T, we will define now the action of an operator curly A on T by the following. Curly A on T is now a new tensor field, a 0k tensor field, which is formed by linearly combining tensor field T or variants of that. How do you do that? You essentially define curly AT acting on a bunch of vector fields x1 through xk in the following fashion. You have a sum over all the permutations in sk. So you're actually going to carry out all possible permutations of k objects. And there, you're going to start with the same tensor T, the 0k tensor that we are talking about, but you're going to permute the arguments. Instead of x1 through xk, you're going to use x sigma 1, x sigma 2 and so on up to x sigma k. Multiply the resulting function by sg and sigma. So a plus 1 if this is an even permutation, minus 1 if this is an odd permutation. Sum up all of these and then divide finally by k factorial. Now, it's rather obvious to see that curly AT is going to be completely antisymmetric. It is a 0k tensor field. That's sort of obvious because you started with T, which is a 0k tensor field, and all you're doing is linearly combining a lot of tensor fields together. It is going to be differentiable because the original T is differentiable. And now, because of its construction, it is designed to be completely antisymmetric. So, this is a K-form. Now, this curly A operator, the so-called alternating operator, has certain rather obvious properties. If T and S are both 0k tensor fields, then curly A acting on T plus S is going to be curly A T plus curly A S. Now, if T is a 0k tensor field and F is a function from the manifold M to R, then curly A acting on the function F times T is going to give you F times curly A acting on T. And another very important property, and that's something sort of obvious from the definition, is if T is already antisymmetric, then what is going to happen is that in each of these you have interchanged the arguments multiple times. If you have done that an even number of times, which is of course what you do when you have an even permutation, then you will end up with an overall plus sign. That is, this expression is going to be the same as T with x1 through xk as arguments. And now, for that you are actually multiplying by sg and sigma, which is plus 1. On the other hand, if the permutation happens to be odd, that means that you are actually carrying out an odd number of interchanges, and each interchange gives you a factor of minus 1. So overall you get a factor of minus 1 from here, but the sg and sigma in that case gives you another minus 1. So what happens is, irrespective of whether the permutation is even or odd, each one of these terms here happens to be exactly the same as T acting on x1 through xk. So when you are adding this up, what you are going to get is all the elements in the permutation group will give you the same term. So this is just going to be multiplied by the number of elements in the permutation group, or just the number of permutations of k objects, which you all know is k factorial. And the 1 by k factorial outside this expression is essentially designed to cancel that. So if T happens to be completely antisymmetric to begin with, then curly AT actually gives you back T. And this of course also means that if you apply curly A twice, the first time, whatever tensor it was acting on has become completely antisymmetric. The next time you apply curly A to give you curly A square, you are not going to get anything new. Whatever happened in the first step, this complete antisymmetrization, if you keep on doing it over and over again, no further change is going to occur. So curly A square as an operator is the same as curly A. Now this is going to be very important. In fact, all three of these properties are going to be very important in deriving many properties of these differential forms. Now, One important point is something which we have already seen before. The set T0Km of all 0K smooth tensor fields on the manifold is actually a module. It's not a vector space with functions as multipliers simply because functions don't form an algebraic field. They only form a ring. This is something we have already discussed before. However, the set lambda Km, which is a subset of all of these, which is the set of all K forms, so not all smooth 0K tensors, but only the antisymmetric ones, it's easy to see that that set is closed under addition and so on, and actually they form a submodule. It's a module in its own right. As a result, the sum of two K forms is a K form. The product of a K form with a function is also a K form, and so on. But what is important is that if you take a K form and say a L form and form the tensor product, you do get a 0 K plus L tensor, but that is not a form because there is no guarantee that that's going to be antisymmetric. Remember, in this case, what you're going to end up with is a 0 K plus L tensor. That means that it will require K plus L vector fields as arguments. Of these, the first K vector fields are going to serve as arguments for the first K form in the tensor product, and the next L, the final L vector fields, are going to serve as arguments for the second L form in the tensor product. Now, this product is going to be antisymmetric in the first K factors and in the last L factors, but there is absolutely no reason for it to be antisymmetric when you interchange one of the first K arguments with another of the last L arguments, because they are ultimately going to different forms. However, in order to produce a differential form, you must have an object which is completely antisymmetric in all its arguments, not just the first K taken separately or the last L taken separately, but all possible interchanges should give rise to a minus sign. That is what is not going to happen when you take a tensor product of a K form with an L form. But there is another obvious way in which you can actually end up producing a form by modifying the tensor product of a K form and an L form. So if we have a K form omega and an L form eta, then this product that we alluded to right now, the so-called wedge product or exterior product, written omega wedge eta, is defined in the following manner. We already know that by taking the tensor product of omega and eta, we are going to produce a 0 K plus L smooth tensor field. And we know how to produce a K plus L form out of that. Just use the alternator, curly A. So, omega wedge eta is defined to be curly A acting on the tensor product of omega and eta. So, we are going to end up with a K plus L form given a K form and an L form, and this is basically like the tensor product but with the additional antisymmetrization. Now, note that some authors actually use a slightly different definition for the wedge product. They carry out the alternation, of course, but then multiply this by a prefactor given by K plus L factorial over K factorial times L factorial. Now, this additional factor essentially serves to make some equations that we will see later on turn out to be simpler. However, they have the disadvantage that they make other expressions more complicated. So, on the balance of it, there is nothing much to be gained by putting in this extra factor, but you have to be aware that certain authors do use this. So, if you're consulting some textbook, you should make sure which particular definition of the wedge product is being used there. Now, what is important and rather obvious from the construction is that if omega is a K form, member of lambda Km, and eta is an L form, then omega wedge eta is a K plus L form. Another result which is pretty obvious from the basic construction as well as properties of tensor products and so on is that if f is a C infinity m function, that is f is a smooth function, then it's also a 0-0 tensor or a zero form. So f wedge omega, if we just use this definition, is going to be the alternator acting on f direct product with omega. But a tensor product of a function f and a form is just f times omega. And we have already seen that property of the alternator is that f can come out. So this is f times a omega. Remember, omega is completely antisymmetric to begin with, being a form. So a acting on omega is nothing but omega itself. So f wedge omega is f times omega. And you can easily show that that's the same as omega wedge f. So at least if you have a function and a K form, then f wedge omega and omega wedge f are always the same. Another property which is rather easy to prove is that this wedge product plays rather nicely with linear combinations. If a and b are real numbers, omega 1 and omega 2 are K forms, eta is an L form, then the wedge product of a omega 1 plus b omega 2, this particular linear combination with eta, is nothing but a times omega 1 wedge eta plus b times omega 2 wedge eta. So the wedge product distributes over summation. It does so when the sum is on the left. It also does that when the sum is on the right. That is, eta wedge a omega 1 plus b omega 2 would also be a times eta wedge omega 1 plus b times eta wedge omega 2. And if f is a smooth function, then f omega is also a K form, and f omega wedged with eta is the same as omega wedged with f eta, both of which are actually equal to f the function times the wedge product of omega and eta. Now, our next result is very important, but it's not that easy to show in general. So I'm not going to spend a lot of time proving that, but you should be able to convince yourself with some simple, at least small K forms, that this is actually true. That if you have three forms, a K form, an L form, and an M form, alpha, beta, and gamma respectively, then their exterior product is associative. Alpha wedged with the product of beta wedge gamma is the same as alpha wedge beta wedged with gamma. And each of these is actually the same as what you would get if you were to carry out the tensor product of alpha, beta, and gamma and apply the alternator operator on the overall tensor product. So, exterior product is associative. This is a property it shares with ordinary multiplication. But one thing which is very different is that it is not always commutative. Note that the one example that we have seen before, that of a zero form and a K form, f wedge omega, is exactly equal to omega wedge f. So in this particular case, it is commutative. However, say if alpha and beta were two one forms, then looking at the definition of the wedge product, we know the following. Alpha wedge beta, this two form, when fed with two vector fields x1 and x2, the result is of course the same as this, which is the definition of alpha wedge beta acting on x1, x2. But the alternator essentially works this way. This alpha wedge of beta operator will be given x1, x2 as arguments, and alpha wedge beta will also be given the other permutation. In this case, there are only two permutations of two objects, x2 and x1, but this one will come with a minus sign. And of course, you have this 1 by k factorial, in this case 1 by 2 factorial outside. Now this expression, alpha tensor product with beta acting on x1, x2, is by definition alpha acting on x1 times beta acting on x2, the product of these two functions. And this, again according to the same definition, is alpha acting on x2, beta acting on x1. Now, the second term can also be written down as beta tensor product with alpha acting on the same arguments x1, x2. Note that this is of course beta x1 times alpha x2, which this is exactly equal to. So you can write this term as alpha tensor product beta acting on x1, x2 minus beta tensor product alpha acting on x1, x2, or the overall thing is half alpha tensor product beta minus beta tensor product alpha acting on x1, x2. This works no matter which x1, x2 you use, and that means that alpha wedge beta for two 1 forms. Please note that this is the result for two 1 forms and not a general result for any K and L forms. For two 1 forms, alpha wedge beta is basically half of alpha tensor product with beta minus beta tensor product with alpha. And from this expression it's obvious that if you were to interchange alpha and beta here, that is, write beta wedge alpha instead of alpha wedge beta, you are going to get an overall minus sign. So alpha wedge beta is negative for beta wedge alpha. So this is an example of a situation where the two forms anti-commute. Note that the wedge product is not always anti-commuting or always commuting. For a 0 form and a K form, it's commuting. For two 1 forms, it's anti-commuting. In fact, these two are special cases of a more general result. But before I say that, let's take a look at a slightly more complicated example of the same kind of argument. If alpha is a 1 form belonging to lambda 1m and beta belongs to lambda 2m, so it's a 2 form, then how do you calculate alpha wedge beta acting on 3 vector fields? Remember, alpha wedge beta should be a 3 form, so it takes 3 vector field arguments to return a function. Again, by definition, this is alpha tensor product beta with the alternator acting on it. That's alpha wedge beta, and you have given it the arguments x1, x2 and x3. Now, by definition, there is going to be a 1 over 3 factorial. 3 factorial being the number of permutations with 3 objects here. And what you do is you feed the same alpha tensor product beta with these arguments, but not only these, but all possible permutations of this. All the 6 possible permutations, x1, x2, x3, x2, x3, x1, x3, x1, x2. These two are actually even permutations. You cannot go from here to here, x1, x2, x3, to x2, x3, x1 by carrying out only one interchange. You have to carry out 2 interchanges. And here on the other hand, this is what you get when you carry out one interchange. This one, for example, is when you interchange x1 and x3. This one is when you interchange x1 and x2. This one when you interchange x2 and x3. So these 3 terms are results of odd permutations. So you get a minus 1 in front. So this is what the whole thing is. But notice, by the definition of the tensor product, and alpha being a 0-1 tensor, a 1 form is a 0-1 tensor, and beta being a 0-2 tensor, alpha gets the first argument, beta gets the next 2 arguments. So this is alpha x1 times beta x2, x3. That's this. This one is alpha x2 times beta x3, x1. This one is alpha x3 times beta x1, x2. So that's what you have on the top line here. This, and this term. The ones with the minus sign, well, they're also similar. This is alpha x3 times beta x2, x1. Then alpha x2, beta x1, x3. Alpha x1, beta x3, x2. But note that if you compare, say, this term here with this term, both of which have an alpha x1 factor, the beta has basically the same arguments, but here beta has x2, x3, here it has x3, x2. One interchange. That means this is negative of this. But you also have a minus sign from the permutation sign. That means this overall term is the same as this term. In fact, you can easily convince yourselves that this one is the same as this one, with the minus sign taken into account. This one is the same as this one. So actually what you have is twice the top row. And the 1 by 3 factorial now simply becomes 1 over 3 after cancelling out a factor of 2. And this is what you end up with. Now you can do an exactly similar calculation. I'm not just showing you the details of that simply because it's going to be rather trivial to work out and you should really try to do it yourself. If you took beta wedge alpha and fed it the same 3 vector fields x1, x2, x3 and followed the definition thoroughly, you will end up with exactly the same expression. That means that if alpha is a 1 form and beta is a 2 form, then also the wedge product commutes. Now let me state the general result. If you have a K form and an L form, alpha and beta respectively, then alpha wedge beta and beta wedge alpha are related in the following manner. There is an extra factor which is minus 1 to the power K times L. Notice that if either of K or L or both are even, then KL, the product here, is an even number and therefore minus 1 to the KL is plus. So if either one of alpha and beta is an even order form, then the wedge product of that with any other form is commutative. On the other hand, if both alpha and beta have ranks which are odd, so both K and L are odd, only then will the product KL be odd and minus 1 to the KL will give a minus sign. So the rule essentially is very simple. If even one of these forms is of even rank, then the wedge product commutes. If both of them are of odd rank, then the wedge product anti-commutes. But let me remind you that we have not really proven this final statement yet. We have just stated this. The 3 examples that we have seen of a 0 form with a K form, 2 1 forms, and a 1 form with a 2 form corroborate this general formula, but that of course is not really a proof of this general formula. The easiest way to prove this would be to use coordinates. So let us first take a look at what a K form looks like when you use a coordinate chart. So in a coordinate chart u, phi with x1 through xn as coordinates, we can write a K form which is also a 0K tensor in the following manner. Omega, this K form, is simply omega I1 through Ik times dx I1 tensor product with dx I2 tensor product with dx I3 and so on right up to tensor product with dx Ik. This is something you can do with any 0K tensor field. Now omega, these component functions are simply given by omega acting on del del x I1, del del x I2 and so on all the way up to del del x Ik. Now let us take into account the fact that omega is a K form. So it's not only a 0K differentiable tensor field, it's also completely antisymmetric. What that of course means is that the component functions omega I1 through Ik is going to be completely antisymmetric in the indices, in all of their indices. That is, if you were to interchange 2 of these indices Ia and Ib to Ib and Ia, you are going to get a minus sign. That's easy to see because all you're really doing here is applying omega on del del x I1, then del del x Ia, del del x Ib, and finally del del x Ik to get to this. If you were to interchange these two, you would actually get this factor without the minus sign, of course. But if you were to interchange these two, because of the complete antisymmetry of omega, you will get a minus sign, which is of course the minus sign sitting here. Now, the fact that omega I1 through Ik is actually completely antisymmetric in all the indices has this very important consequence. Omega, after all, is already completely antisymmetric in all the argument vector fields. So, if you were to apply the alternator on it, nothing is going to change. Omega is going to stay the same. So, omega is simply going to be curly A, omega I1 through Ik. This is of course a function, times dx I1 tensor product with dx I2 up to tensor product with dx Ik. So you are going to end up with omega I1 through Ik being pulled out. That's just a function, it's pulled out, with the alternator acting on this tensor product. But we have already seen before that this actually is nothing but the wedge product of dxi1 with dxi2 with dxik. So omega is omega I1 through Ik, dxi1 wedge dxi2 all the way up to dxik. Notice that this is going to vanish if any of the two indices match. Remember, this is completely antisymmetric as well. Although the wedge product is not necessarily antisymmetric always, as we have just said, wedge product involving two one forms is always antisymmetric. And even if these two one forms were not sitting next to each other, so there were many intermediate coordinate differentials sitting between them, just interchanging these two would always give you a single minus sign. To see why that is, let us take a look at this a bit more closely. In between dxia here and dxib, there would be some, let's say, p different coordinate differentials, and then you will have dxib. Of course, you have the rest of the coordinate differentials, the beginning and the end. I'm not just focusing on that right now. There are p coordinate differentials in between I, b and ia. Now, if you were to interchange this, one way to do that would be to sort of make this jump across each one of these p such coordinate differentials, so that ultimately you will end up with dxib sitting here. So that will give you extra factor of minus 1 to the power p. Each jump giving a minus sign. But now, that's not the interchange. After all, here you have dxia and dxib sitting next to each other. In order to get an interchange, dxia would have to go jumping back to this position where dxib used to be before. So you have to bring dxia here. But note that when it does that, it has to jump across the original p dx's which are there, but also the dxib first. So you have to actually jump across p plus 1 coordinate differentials to get to where dxib was before. And therefore, the overall number of interchanges is actually 2p plus 1. And so it's an odd number of interchanges, an overall minus sign. Now that is perfectly consistent with the fact that omega I1 through Ik actually would be completely antisymmetric in all the indices. So you are ending up contracting an object which is antisymmetric in all its indices, the omega I1 through Ik, with this wedge product, dxi1 wedge dxi2 all the way up to dxik, which is again completely antisymmetric in the indices. Now, one immediate consequence of this is that if the rank k of a k-form is more than the dimensionality of the manifold, then the k-form must identically vanish, because then no matter what I1 through Ik you choose, there will always have to be at least two which match. Simply because you don't have that many different values of i's to put in. You have only n distinct i's you can put, and if k is more than n, you will run out of distinct indices to put in. So at least two of the indices will match, and whenever that happens, you are going to end up with a 0. Because if you interchange those two indices, you should get a minus sign, but you should also get the same thing, because you are after all interchanging two exactly identical things. And therefore, the only way you can get a negative sign and still not change is that you have a 0. Now, let us try to write down the wedge product between a K form and an L form by using their coordinate representations. This is the coordinate expression for a K form. If you have a K index bunch of functions as components, but instead of a tensor product dxi1 tensor product with dxi2 up to dxik, which is also the same thing here, you actually are going to end up with dxi1 wedge dxi2 all the way up to dxik. Now this is something that I can always express any k form as long as you are within a particular coordinate patch. So if omega is a k form and eta is an L form and we are using coordinates, omega can be written in this form, omega I1 through ik dxi1 wedge dxi2 up to dxik. Eta similarly can be written down in the form eta j1 through jl dxj1 wedge dxj2 up to dxjl. So we want now to see what happens when you interchange eta and omega in the wedge product. Let's start with omega wedge eta and then we are going to slowly go through an interchange. So first, this is omega and this of course is eta, and we are going to do a wedge product of both of them. Now because omega I1 through ik and eta j1 through jl are functions, they can be pulled out of this wedge product. So you end up with omega I1 through ik, there's this factor, times eta j1 through jl, times the wedge product of dxi1 through dxik, then a wedge with dxj1 through dxjl, what we have written here. Now, in order to see what happens when you interchange eta and omega, what we will do is bring this whole bunch of dxj's to the front, ahead of the dxi's. So let's do that one at a time. If you were to move the dxj1 all the way here, you will have to actually jump over k dx's. And remember, the wedge product of two one forms is anti-commuting. So every jump gives you a minus sign. So you end up with an overall factor of minus 1 to the k when you end up with this dxj1 moving from here to here. Of course, that's not your complete task because you still have dxj2, dxj3, etc. to jump across. Now, if you also brought dxj2 over, what will happen is simply you will end up jumping this dxj2 over exactly k1 forms all over again, incurring minus 1 to the k more factors. So you are going to end up with minus 1 to the 2k. Now, of course, your job now is to make each and every one of the dxj's jump and sit in just the right order on this side. So each one of them has to cross exactly k such one forms. So each time a dxj jumps across, you get a minus 1 to the k, but you get that L times once for each of the dxj's which jump. So minus 1 to the k times minus 1 to the k and so on all the way up to L, minus 1 to the power k whole to the power L, and therefore minus 1 to the kl. Now, once you have done that, you can of course push the etas inside here and the omega inside this, and now you have eta wedge omega sitting here. So what we have ended up proving is omega wedge eta is minus 1 to the kl times eta wedge omega, the result that we had alluded to before, which tells us, let me remind you once again, that the wedge product of an even rank form with any other form is always commuting. The wedge product of two odd order forms is anti-commuting. Now there's a lot more to be said about differential forms, their algebra and their calculus, and we will have to develop this over a series of lectures. But let me end today by giving you an illustrative example of some kind of calculations, the kind that we have talked about, using a rather simple setting. Let us talk about a manifold which is perhaps the simplest manifold that we are all familiar with. Let's say M, the manifold, is simply R3, the Euclidean three-dimensional space. And let's say the coordinate chart that we use is basically the Cartesian coordinate chart. That is, the domain is the entire set and the coordinate functions are simply x, y, z, the familiar three-dimensional coordinates. Now this being a three-dimensional manifold, the maximum rank form that you can have here is 3. You can have a 0 form, a function, a 1 form, a 2 form, and a 3 form. And we will interpret these 2 forms, 3 forms, etc. in detail later. But for the time being, let's just point out that dx, dy, dz are your coordinate differential covector fields or coordinate differential forms, and therefore the basis for, say, the set of 1 forms, the set lambda 1, is going to be dx dy dz. Any one form, omega, will be a linear combination of these. So it could be alpha dx plus beta dy plus gamma dz, where alpha, beta and gamma are smooth functions. When you go over to lambda 2, then you will have dx wedge dy, dy wedge dz, and dz wedge dx as the basis vectors or basis 2 forms. Any 2 form would be a linear combination of these. Notice the dx wedge dx is identically 0, so those terms don't exist. And dy wedge dx is essentially dx wedge dy with a minus sign, so you don't count that separately. So any such form, let's say a 2 form, would be of the form f times dx wedge dy plus y times dy wedge dz, so plus g times dy wedge dz plus say h times dz wedge dx. Again, f, g and h are functions. Finally, you have 3 forms, which is the highest category possible here. And there, the basis 3 form is simply dx wedge dy wedge dz. Of course, you could have used any other permutation. You couldn't repeat the dx's, but you could have used any other permutation. But they are basically the same as either this one or this one with a minus sign. So the most general 3 form, beta, would be, let's say, some function u times dx wedge dy wedge dz. Now, in order to show that the wedge product that we have defined actually would in this case give us rather familiar entities, let's talk about 2 one forms. Let's say P, which I could have of course written as alpha dx plus beta dy plus gamma dz. Instead of that, let's call that px dx plus py dy plus pz dz. Now, if the notation here reminds you of components of a vector, that's not entirely an accident. But we are going to talk about the connection between vectors and these one forms in some detail later. For the time being, let's just treat this as a notation. Q, another one form, qx dx plus qy dy plus qz dz. Now, let us just form the wedge product of these two, P and Q, by going through the standard definition. So, one thing we know is that you have to take the wedge product of this whole thing with this. And there you have distributivity, both to the right or to the left. So, px dx distributes over all 3 factors. But notice, px dx which qx dx is going to give you 0. Dx which dx is of course 0. So, you get px qy dx wedge dy plus px qz dx wedge dz. So, these are the 2 terms you get when you wedge this with the whole thing. When you take this term and wedge it with the whole thing, this term, the wedge product of py dy with qy dy will drop off. But you will get plus py qx dy wedge dx. Note that the wedge product is not commuting in general, and in this particular case, where we are actually commuting to differential one forms, it's definitely anti-commuting. So we have to be careful about the order. Py dy wedge qz dz, that's py qz dy wedge dz. Finally, if you look at the third term here, pz dz wedged with the whole thing, you get pz qx dz wedge dx, once again maintaining the order, plus pz qy dz wedge dy. pz qz dz wedge dz is of course 0. But now, you apparently get 6 terms here, but you really don't, because this and this are related by a minus sign. So this is just px qy minus py qx dx wedge dy. You can of course write down the other 2 terms very similarly by collecting terms here together. But even this one term should be reminiscent of something you already know. this quantity pxqy minus pyqx should be quite familiar. If you have two vectors with px, py, pz and qx, qy, qz as components, this would really be the z component of the cross product. So the wedge product that we have talked about can be seen as a generalization of the cross product, because after all, in the special case where you have two one forms, it's essentially replicating the cross product. Well, not only that, by taking a wedge product between a one form and a two form, you would actually be able to replicate the dot product as well. I will just leave that as an exercise for you. But notice that the two major operations that we learned about in vector algebra long ago can both be seen as essentially being two sides of the same coin. The wedge product takes care of both of them together. Now this kind of unification happens all the time when you are using differential forms. Operations which look like different operations come together and end up being interpreted as the same operation applied to different order forms. We will see much more of this later. This is just the beginning. This at least should be enough to pique your interest in this subject. Differential forms actually give us a way of unifying a lot of the maths that we have done in earlier classes. So even when you're talking about something as simple as just plain three-dimensional Euclidean space, even in such a simple setting, differential forms actually have a lot to tell us. But much more on that will come in the next few lectures. Bye for today.